This is the Chapter 9 podcast on energy, and this is a very long chapter. I think there's about 10 sections in it, so let's get started. This first slide talks about Newton, and one of the things that Newton actually missed was energy. He didn't quite get it. He got his 3 laws of motion, but missed energy. So the big idea is that energy can change from one form to another without a net loss or gain, which incorporates a lot of things. That energy has a lot of different forms, and that there's also a conservation of energy, just like we saw an idea of conservation of momentum. So, and we see energy transferred from place to place all the time. Right there you're seeing a picture of a windmill, and the wind is going to blow the windmill and use the energy of the kinetic energy of the wind, and then it's going to be transferred probably into electrical energy through a generator at some point. And that's a theme that we're going to see throughout this chapter. So the first section, 9.1, is on work, and work has everything to do with force and distance that an object moves, and we'll see that more clearly when we see the actual mathematical definition of work. So, what is work? Well, work essentially is force times distance. So we say that work is the product of of force times distance. So it's the force we apply to an object and how far we apply that force as we move the object. And a good example is when we lift something against the Earth's gravity. We're applying a force on the object, which is probably going to be equal to their weight, and we're lifting it. The higher we lift it, the more work we're going to do with that on that object. And we this is just a restatement of it, and you can see we're going to use the letters capital W for work, and capital F for force, and lowercase d for distance. If you lift 2 different loads and we compare them, you're going to do twice as much work if you lift 2 objects at the same time, say like 2 boxes or 2 books, as opposed to 1 object, because it's twice the force, it's twice the weight. And if you lift the load twice as far, then you're going to do twice as much work because the distance is twice as great. And here's a weightlifter lifting a dumbbell, and once again, if he lifts it twice as high, he would have to do twice as much work. But looking at the weightlifter lifting the barbell over his head, once he gets it over his head and he's holding it still, he's not doing any work. His muscles are contracting, stretching, squeezing, but he's not doing any work on the object because he isn't moving it any further distance. Now, here's another example. If you have a waitress bringing a order on a tray, so like soup or something, yes, they initially do have to lift the tray up, but as she moves the tray through the restaurant, she's moving it, the motion of the tray right here is perpendicular to the actual force she's applying on the tray. So therefore, she's doing no work on that tray. So here's some other examples that have to do with when work is done against another force, such as an archer pulling a bowstring. You're doing work against the force of the bow. When you lift a pile driver, that's a very heavy weight that is dropped onto another object. You're lifting that against the force of gravity. And when you do push-ups, like this little baby is doing here, you're doing work against your own weight. There's also work that can be done to change the speed of an object, such as bringing an automobile, accelerating it, or slowing it down. You're applying a force over a distance to make that object speed up or slow down. And another problem with work is that work has to be done in the direction, the force of the work has to be done in the direction of the work. So if you look at this force here, it's actually at an angle. So only the horizontal component is going to be included in the work. This portion that would be right here of the force is not counted. It does not have anything to do with the work. Here's another example. If you whirl a ball on a string, the force on the ball is inward towards the center of the string, but the distance that the ball travels is always perpendicular to that force. So absolutely no work is done on this ball, even though the ball goes round and around. Same thing with the Earth. The Earth does no work on the moon. The force of gravity between the Earth and the moon is actually perpendicular to the motion of the moon. So let's talk about the unit. The unit of work is going to be the unit of force, a Newton, times the unit of distance, meter, a Newton meter. This is also known as a joule. So a joule of work is done when you move a force of 1 Newton over a distance of 1 meter. When you apply a force of 1 Newton over a distance of 1 meter. And this is who the joule is named after. And larger units, kilojoules, that's 1,000 joules. And megajoules are millions of joules. Now let's say we apply a 60 Newton force to a 32 kilogram package, and we push it across 4 meters across a mail-room floor. How much work do you do on the package? Well, the first thing I'm going to tell you is that it's 32 kilograms of red herring in that package, and it's going to be a smelly package full of fish, because there's a number here we don't need. The force, the only thing we're looking for work is the force and the distance. The actual mass of the package is not of concern to us when we're trying to find work. So it's going to be the force times the distance, 60 newtons times 4 newtons, and that'll give us 240 joules. So once again, when is work done on an object? Work is done on an object when a force is applied over a distance to move the object.